all in this presentation related with the subject fundamentals of surface engineering, and you know that we are talking about the characterization of the modified surfaces, and under this we have talked about the metallurgical characterization and chemical composition analysis. In connection with the metallurgical characterization, as you have seen, we basically will try to see the microstructural aspects of the modified surfaces, wherein we see the phase structure and the grain structure. So, in the phase structure we try to see the type of the phases which are present, or types of the micro constituents which are present, and their percentages, their percentage or the relative amount, and where which phase is present, that is about the distribution of phases. So, these are the three aspects. For example, we start with the carburizing of the low carbon steel. We perform the carbon enrichment of the surface layers up to the 0.8% carbon, followed by the hardening. So, when we perform the hardening, is performed by heating the component to the austenitic state, followed by the rapid cooling for having the martensitic transformation. Since the carbon concentration varies from the top to the substrate, the top surface to the substrate layer, so carbon concentration may vary like this. Since the carbon concentration may be very high at the surface layers, and it will be decreasing, like say 0.2, which was already there in low carbon steel, and like say this is about 1% carbon. So, since the carbon content is decreasing with the increasing depth, so accordingly the phases which will be formed at the different zones, increasing depth below the surface, they will also be changing. At the surface, definitely we are going to have the high carbon martensite, but below that we will be having the somewhat low carbon martensite plus some retained austenite. Then thereafter we may have the martensite, low carbon martensite plus perlite, and then perlite ferrite. So, in the different zones, if we take the different layers of the carburized component, we may have the different phases present in the different zones. So, that is what is determined, where which phase is present and what is the approximate percentage or relative amount of that phase. What is the proportion of the martensite, perlite, ferrite in the carburized and a carburized component, and which has been hardened after the subsequent hardening process. This is one aspect wherein we try to look for the types of the phases and their amounts and their distribution. Apart from this, even for the given phase, we may have very large or coarse grains of like say 50 to 100 micrometer, or we may have very fine grain like 5 to 10 micrometer. We know that the coarse grains offer the poor mechanical properties, poor wear behavior as compared to the fine grain structure. So, we need to see that what is the kind of the grain size which is present at the in the different zones of the modified layers. Apart from that, what is the shape of grain? The spherical and equexed grains offer the better resistance to the wear as compared to the needler shape or sharp edged polyhedral shaped large size particles. So, the shape is characterized. For characterizing the size, we have to see the average diameter, like this is the area A, then we can determine the average diameter from pi by 4 d square. So, this area we can determine from the image analysis, and similarly we can determine the like for the dendritic structures, like where we have The dendrites like this, interdendritic arm spacing is used. In case of the cellular structures, intercellular spacing is used. So the different parameters are used for quantifying the grain size. Similarly, for quantifying the shape of the grain, various parameters like aspect ratio or the shape factor or form factor, all these are obtained through the length to the width ratio of a given microconstituent. Like needler shape microconstituents will be offering much greater length and very smaller width as compared to the much greater length and smaller width. So here it may be like 5 to 10 for needle shape structures, while for polyhedral shape it may be like 1.5 to 2 or more. Like this is the length and this is the width. But for the spherical shape products it may be like 0.9 to 1.1, where length and widths are almost same. For wear resistance applications, it is always preferred that microconstituents are of the spherical family or close to the spherical family, where aspect ratio is like 0.8 to 1.2, so that the length and widths are almost same, and at the same time they are fine in size, like 5 to 10 micrometer, very fine size. Microconstituents will be offering much better wear resistance as compared to the like 50 to 60 micrometer grain size microconstituents. So the size and shape, the type of phases, these are the things that we try to quantify. For determining the type of phases, simple microscopy doesn't help, but we need to perform the XRD analysis. So XRD analysis actually helps us to identify the various phases which are present. If we see this typical micrograph, this is for the iron, carbon, chromium, vanadium, molybdenum hard facing, which has been modified by the various the proportions of the Ceria addition. Like this hard facing was developed using the 0% of the Ceria, then this was developed using the 2% of the Ceria, then this was developed using the 4% and accordingly 6%. So if we see the micrograph, we can see this offers a very coarse grain structure, and this is somewhat finer and further finer for this case. So if we perform the image analysis of this micrograph, we find the finest grain size for this kind of composition, where the this base hard facing system is modified with the 4% of the Ceria. Thereafter further addition of the Ceria is leading to the increase in the grain size. I mean to say there can be different compositions, different processes, different processing conditions which will be leading to the different kind of the grain sizes, different kind of the phases, and those need to be identified and established. Similarly, if we see these are the two different micrographs of the same coating. So what it shows that when in as a spread conditions, like say this is the nickel, chromium, boron, silicon flame spread coating developed by the flame spraying, and optical microscopy of this coating primarily shows the nickel solid solutions cells, and in between the black one is showing the eutectic matrix. So if we see the average size of the nickel solid solution cell is coarser, in this case it was around like say 35 to 40 micrometer, while after the grain refinement this size was reduced, and in this case the reduction led to the like 80 to 20 micrometer average grain size of the nickel solid solution cells. So such kind of the refinement is expected to increase the yield strength and increase the hardness, and which in turn will be able to enhance the wear resistance. So it is important through the image analysis to find out the average grain size, the fractions of the various constituents. Here we can determine the fraction of the nickel solid solution cell and the eutectic percentage separately. At the same time, image analysis can also be used to used in quantification of the pores which are present. Like say in this surfacing, we can see this is the base metal and this is the surfacing, and here we can primarily see that the epitaxial growth is there at the interface in the weld surfacing, but at the same time it is having lot of pores. So, to quantify the proportion or the percentage of these pores, the image analysis is carried out, and we found that these pores are about 15 to 16%. So, porosity measurements are also possible through the image analysis apart from using other techniques. As I have said, if the nickel, chromium, boron, silicon coating developed using flame spraying process, as I have said, nickel solid solution cells, and in between we have eutectic matrix. So, there is a difference. This is the SAM image, and earlier what I have shown was this was the optical image. There is a difference here. The nickel solid solution cells are white and the eutectic matrix is dark. And this is the optical micrograph. On the other hand, just reverse, we see when the SAM is taken of the same component, eutectic will be looking white. This is the eutectic mixture is white, and the nickel solid solution cells are looking dark. So, this just the reverse kind of the shades and the colors are achieved when the optical and the SAM is used for the analysis. From this we can simply see the number of microconstituents which are present, their sizes and shapes, but we do not know what it is exactly. So, for that purpose XRD analysis is carried out. XRD analysis helps us to know that there is a nickel boride, chromium boride, nickel silicide, chromium carbide. So, these nickel boride, so these are the various constituents which are present, can be analyzed through the XRD analysis. Similarly, we can do this kind of analysis on the component subjected to the nitriding, and the component which has been subjected to the nitriding will be leading to the formation of the various types of the nitrides like Fe3, N4, Fe2, N3, and which type of the phases are being formed and where these are being formed, that is what can be easily identified through the XRD analysis and the microscopy. Similarly, we can find the borides, the types of the borides and their relative amounts through the XRD analysis and the metallography of the component. In this case, like say iron, chromium, niobium, vanadium, carbon system whose weld surfacing was developed, and weld surfacing was developed by varying the vanadium concentration. In case A, the vanadium concentration was 0. In case B, means LYB, the vanadium was 0.6% and then vanadium was added to 1.5%. So, what happens when the vanadium content is increased in terms of the various phases which are present? If we see, when there is no vanadium, 0% of the vanadium, there is no vanadium carbide formation. Rest of the alloying elements are forming their carbides, and that is what we can see, the presence of the various carbides. Apart from that, there is a presence of the martensite and the austenite in the weld surfacing produced of this alloy system. But when we add the vanadium 0.6%, that is in this case we find that there is a kind of vanadium carbide present apart from the other carbides and the phases which are present, like in this case cementite, niobium carbide, chromium carbide is also present. And when the vanadium carbide is added in 1.5%, then vanadium is added in 1.5%, vanadium carbide is there. The two types of vanadium carbides are there, one is this, another is this. In addition to that, we have chromium carbide, niobium carbide, martensite. and the austenites. So, what are the various phases? Because each phase has the different hardness values and which offers the different kind of effect on the wear resistance. That is why it is important to consider the types of the phases and intermetallic compounds and the carbides which are present in the given modified surface. So, we can accordingly we can anticipate its hardness, its wear resistance under the service conditions as per the requirement. So, for performing the wear test, like say we will be talking about the four types of the wear tests are conducted to check the or to evaluate the resistance of modified surfaces against different types of wear conditions, and this will help us to know that at what rate the modified surfaces will be wearing out under the service conditions against a particular type of the wear. So, that will also help us to estimate the tribological life of the component under the tribological conditions. And based on this we can take suitable decision whether the modified surfaces have will be able to perform the intended function under the actual service conditions or not. The most common types of the wears which are commonly encountered include adhesive wear, abrasive wear, erosive wear, corrosive wear. So, we will be talking about these three types of the wears and the way by which these are performed. As you know, the adhesive wear is performed through the contact between the metal to metal contact. So, in this case we take one modified surface, like this is the modified surface whose wear resistance is to be checked under the adhesive wear conditions. So, the sample of the modified surface is prepared and it is kept against the another counter surface. Now, counter surface will be taken of the suitable material against which the wear resistance we want to check. So, it's the metal system, its hardness, its physical properties like thermal conductivity and thermal diffusivity, and its roughness. All these affect the adhesive wear behavior significantly. So, the counter surface must be selected in light of the application against which wear behavior of the modified surfaces is to be checked. It may be like say it may be hardened steel or it may be cast iron. As per the application, the suitable counter surface is selected so that it has the required hardness. Then we'll be smoothening it to the required level. Normally the counter surface is smoothened to very high degree of finish like 0.2 roughness value. 0.2 RAA is the roughness value, and against this counter surface it is usually in form of the disc which is hardened ground, smoothened finished, and against this we place the sample of the modified surface whose wear resistance is to be checked, and then we apply the normal load. So, basically against this disc the specimen is kept and we apply normal load. This normal load may be like 10 Newton, 20 Newton, 30 Newton, and this one is selected according to the application. We have to see what will the kind of the contact pressure during the service, and accordingly we select the suitable load, and then the relative movement is given between the two. After applying the load, holding the specimen over the counter surface, relative movement is given to the counter surface. in such a way that the direction of the movement can be unidirectional, like in case of the disc, or it can be reciprocating type. So, accordingly we will be having the two types of the configurations. One is where the pin is kept on the disc which is rotated. This is commonly known as POD. The disc like this and pin is kept over the disc in this manner, and then we apply load and the disc is rotated. So, this kind of configuration is called pin on disc. Then there is a pin on flat or pin on plate. In case of the pin on plate, the material of the counter surface in form of the flat plate, the pin is kept under or pin is held over the counter surface and the required normal load is applied, and then it is reciprocated. So, there can be unidirectional movement through the rotation of the counter surface, or there can be reciprocating relative movement between the pin and the plate through the reciprocation of the plate. Now, what will be the velocity or the relative velocity between the two? So, the relative velocity basically determines the sliding speed or sliding velocity. As per the application, this may be kept in the range of 0.2 to 0.5. This is the normal operational speed. This is in mm per second. For high, if the modified surfaces are to be used for the higher relative movement conditions, then of course we will be going for like 1.5 0.5 to 1 meter to 2 meter per second sliding speed. So, the pin will be kept at a fixed location while the counter surface will be rotated at the different speeds for achieving the required sliding speed. Now, there is one more additional aspect, like this is the disc, this is the center. So, this is the location, or you can say the wear track, where like say this is where a pin has been kept and the disc is made to rotate. So, this the wear track diameter d, the rotational speed n determines the sliding speed. So, sliding speed is obtained from the pi dn divided by 60, because n is the rpm, d is the diameter in mm, or it can be in meter, for if you want that the sliding speed is obtained in the meter per second. So, if the d is in meter and n is in rpm, revolution per minute, then divided by 60 will be giving us meter per second sliding speed. So, there are two important parameters, one is the load and another is the sliding speed under against which the wear test is being performed. Apart from this, the rotational speed and wear track diameter, like say if the wear track diameter is very small, then the time for dissipation of the heat from the wear track will be very small as compared to the case when the wear track diameter is large. So, in this case it will take longer time for given RPM, it will take longer time to get the particular location of the counter surface come across the frictional effect. So, here there will be more localization of the heat and here less localization of the heat. So, rise in temperature of the counter surface affects the wear behavior. So, even the wear track diameter can be important in affecting the wear behavior of the material. There another parameter is the sliding distance, like for a given at a given location, for how long this the test is conducted, so that the continuous wear of the material is taking place. So, if we plot one typical sliding distance versus the wear plot, then we may notice that initially wear is changing as a function of distance, and then it becomes constant. So this corresponds to the initial stage, corresponds to the run in period, and this is the steady state period. For adhesive wear, the test must be conducted for long enough period so that we achieve the steady state, and this will be indicating that what is the kind of the material loss for unit sliding distance. That is what the slope will be indicating. So that the conditions against which the test is being conducted, like the wear, which is quantified maybe in terms of like gram per meter or cube per meter, that's how the wear rate is achieved, and then and this wear rate is to be reported along with the value of the load, velocity, the kind of the counter surface material, the sliding distance, the temperature realized. We know that during the sliding there will be continuous rise in temperature. So sometimes measuring the temperature of the wear pin at different locations also helps in explaining the wear behavior. So normally we insert the thermocouple at different locations, increasing distance from the sliding surface, sliding interface, like say at the interval of 1 mm, and then we try to plot like say 1, 2, 3, 4, 5 mm, 5 different thermocouples inserted at 5 different locations, increasing distance from the surface. So 1, 2, 3, 4, 5, increasing distance from the sliding interface, and then here we plot the temperature value. We mention the temperature value. So obviously at the interface we don't have any thermocouple for measuring the temperature at the interface. So temperature at location 1 at location 1 at 1 mm distance from the sliding interface is located on the plot, and then for 2 mm, then 3 mm, then 4 mm, and then 5 mm. This is how it is plotted. So this will be giving us the trend of variation in temperature, and extrapolation of this will help us to get the value of the temperature at the interface, and this temperature of the interface value can be useful in explaining the friction and the wear behavior of the modified surfaces which have been used. So now likewise, instead of the metallic plate like here on the counter surface, we can fix the abrasive paper over the disc, and then we mount the wear specimen or the wear pin. So in that case, the wear pin or the pin on drum or the pin on the flat, in all these cases the metallic plate is replaced with the abrasive medium or abrasive paper, and thereafter the same method is repeated. So instead of the rubbing of the modified surfaces against the metal, in this case the rubbing will be happening against the emery paper for assessing the wear behavior. So that is what we can see here. This is the pin on disc arrangement, this is the disc rotation of rotating disc, and this is the wear pin whose wear resistance is to be checked. We apply the normal load and the counter surface is rotated, and we take the initial weight and then final weight, difference of 2 will be giving us the wear or the weight loss. Weight loss may be divided with the density to check the wear in terms of the volume, wear volume. This is the wear test setup for a reciprocating kind of the arrangement. So in this case this is just the arrangement for holding the workpiece and applying the normal load. The main thing is here where in this sample is held against the counter surface. This is the counter surface, and counter surface is made to reciprocate, and this counter surface for reciprocating adhesive wear, again under the reciprocating conditions, this will be the metallic surface, and otherwise this metallic plate will be covered with the abrasive medium, so that the modified surfaces or the wear pin sample will be rubbing to the abrasive medium. This is the simple concept of the reciprocating configuration of the wear test. So the counter surface is placed with the abrasive medium, and against which the component whose wear resistance is to be checked is kept under the normal load, and then reciprocating movement is given. Whenever this kind of thing is done, we will be having the possibility that the wear debris particle is left at the interface, and which will be increasing the tendency for the increased wear due to the 3 body wear conditions. In case of the 3 body wear condition, like say this is the sample to be tested, and this is the standard rubber wheel, and this sample is pressed against the rotating rubber wheel, and in between that we feed the sand particles. So rubbing of the sample against the rubbing wheel while the sand particles are coming in between will be causing the 3 body abrasive wear conditions, and this test corresponds to the ASTM G65. In this case also we will be measuring the initial weight of the sample and the final weight of the sample, and difference will be giving us the weight loss. And here we can check the wear rate in terms of the wear loss per meter, or the kind of the load which is being applied for the unit weight loss, like the weight loss against the 100 gram or weight loss against the 200 grams. So, it's a very less load is used under the abrasive wear conditions as compared to the adhesive wear conditions, because wear happens at very high rate under the abrasive wear conditions. Now, I will summarize this presentation. In this presentation, basically I have talked about the importance of the microstructural aspects with regard to the wear behavior, and also I have taken up the 2 types of the techniques which are used for assessing the wear behavior. One was the ways by which we can assess the adhesive wear behavior of the material, and another was about the methods which are used for assessing the abrasive wear behavior. Thank you for your attention.